Still on advanced and applied linear algebra, we'll be looking at linear algebra in computer graphics. In the last video, we considered linear algebra in data science, and we saw how linear algebra helps to talk about feature space, principal component analysis, and even regression in data science. So this is another application of linear algebra in computer graphics, and it's really important. So computer graphics uses linear algebra to move, rotate, scale, and project 3D objects onto a 2D screen. So in the process of learning linear algebra, right, we got to that point where we're talking about rotation, scaling, and all that for geometric for using points for starters. So there are two fundamental concepts in this case of linear algebra in computer graphics, and they include transform pipelines and homogeneous coordinates. Together, they allow all geometric transformations to be expressed using matrices. So at the end of the day, all those graphics thing you're doing, working with pictures, videos, and all of that can actually boil down to matrices. So let's start by looking at transform pipeline. So a transform pipeline is the sequence of coordinate changes that converts a 3D object into a 2D image. All right. So the transform pipeline can be shown as starting from a model space, it comes to the world space, then it goes to the view space, goes to the clip space, goes to NDC, and then screen space. Each stage applies a matrix transformation. So once an object is rotating, for instance, there are so many shape changes happening right there. So talking about the pipeline stages, like we mentioned up there, for instance, we have the following. The first step, you have the model. So stage one, you have the model space, and there you have the local object coordinates, like maybe X and Y axis, or if it's three-dimensional, you have X, Y, Z axis. Then at the second stage, you have the world space. Then you have the global scene coordinates. And at stage three, you have the view, which is some kind of camera relative coordinates. And then at stage four, you have the clip that comes after projection. Okay. In projection, like we saw on the Gram-Schmidt orthogonalization, it's more like you're stretching out vectors to become perpendicular. So, and that's what happens when you do the Gram-Schmidt process, for instance. And at the NDC level, you have normalized device coordinates. Okay. And finally, you see the screen space where you have the pixel coordinates as you see things on the computer screen and all of that. Symbolically, so from model space, you move to world space, you move to the view space, you move to the projection, and then you move to the screen space. Okay, so talking about the model space now, model space to how do we move from the model space to world space? Then we talk about the model matrix. So the model matrix places an object into the world. It can include things like scaling, rotation, translation, and we saw all of that, in a previous video. In fact, I always like to refer to that. I think I have that on my desktop, for instance. If you look at this, so first of all, this is reflection. This is what reflection looks like, you know, and this whole thing started with points. So all these points now. So there's a way you vary the signs and do all that. So and you get something new. So this is for reflection now. So beyond reflection, you have rotation. So you have rotation right here. Next, you have apart from rotation, you have scaling. All right. So same object, but then you scale it up. Then you have shear, so that's like some kind of stretching out and all that, stretching along the vertical or horizontal axis. So we see all of this happening, and this is how we can have imaging. So it includes scaling, rotation, translation, and all of that, or even shear, like you saw right there. So an example of this, if you want to translation by 320 now. So translation by 320, imagine you have this T, you have T, and then you have a point 0001. So this is a 4 by 4 matrix, right? And you're translating by 320. So you have point P, which is 0001. So after the transform now, you have P prime, which is TP. That is, you multiply T by P. So if you multiply T by P, you end up getting this 3201. So that gets rid of every other thing apart, and then you're only left with this 3201 right here. Of course, that's matrix multiplication right there because we're working with TP. So you have 1003 against 0 0, 1, 0, 2. So you want to multiply all of this by, so this is a 4 by 4 matrix, and this is a, so you have to make it the vertical, okay, T comes first, right? So you have TP, so you make this the column matrix. So you have a 4 by 4 by 4 by 1. At the end of the day, end up getting a 4 by 1 matrix, like what you have right here. So then what about movement from world space to view space? In that case, you need a view matrix. In the first case, you needed a model matrix. Now you need a view matrix as you move from world space to view space. So the view matrix represents the camera. Instead of moving the camera, we move the world in the opposite direction, right? So an example of that, imagine a camera at the point 005, and you want to translate world by 00 - 5. So you have V, for instance, and then you have your V right here. So like this. So first of all, it looks like you have a unit matrix, but because you have this fourth part like this, so you have 0001 like this with that 00 - 5 right here. And the camera, so the camera is at 005. And just like we said that instead of moving the camera, we move the world in the opposite direction. So in the opposite direction, you have 005 becomes -5 like that. Okay, so that's the view matrix. And then talk about view space to clip space. To move from view space to clip space, you have the projection matrix. Okay, so projection maps 3D space to 2D space. So perspective projection makes distant objects appear smaller. Conceptually, you can then have that XYZ. It can then be mapped to X over Z, comma Y over Z. So this is implemented using a projection matrix. And of course, remember we talk about projection a lot under orthogonality and transform and approximations, I think. So, and then you move from clip space to screen space. The steps here, you have to divide by W. That is perspective divide. And then you normalize to -1, 1. And then you map to screen pixels. So, and the perspective divide now has become something like X sub NDC equals X prime over W prime Y NDC, while YNDC is Y prime over W prime and ZNDC. Okay, I think that these ones should actually be different. They are not together like that. So let me separate for proper, uh, so that we can get the things. Yeah, so this is more like what we have. So these are perspective divides now. So you have X sub NDC equals X prime over W prime. Y sub NDC is Y prime over W prime. Z sub NDC is Z prime over W prime. And then you have the MVP matrix now. So all transformations combine into one. So everything you've been doing at the end of the day, it's like everything happening together. So you have what you have on the screen is the initial P, is the final P, right? With the V. So P is the projection matrix multiplied by the view matrix multiplied by the model matrix, and then the original model. So you have the original model, right? The model matrix works on it, followed by the view matrix, followed by the projection matrix. And then that's the P, the object you now see on the screen. All right. This is called the MVP matrix. So MVP is equal to PMV. So like in that order. So in that order, model matrix, view matrix, projection matrix, and then you have the screen. You have the what you see on the screen. Now, for the example of transform pipeline, I imagine that P is 1, 2, 1, 1. So you have operations, you have possible operations like scale by 2. You can double all that. You can translate 300, and you can camera at 005 like that. So talking about the scaling for step one, imagine you have 1, 2, 1, 1, right? So if you multiply by, okay, 1, 2, 1, 1. So you have S to be 200, 200, 200, 00, 20, and 0001. So P1, so P1 is actually S multiplied by P. So this is S multiplied by the column vector 1, 2, 1, 1. So you end up getting, okay, or is even the column vector? This is 4 by 4 multiplied by, yeah, so multiply that, you have 2, 4, 2, 1. So by the column vector, you have 2, 4, 2, 1. And that's the first step of scaling. The next thing you translate. So for translation now, so from what we saw previously, so for translation, you have 100. So you have that unit matrix, right? And for the translation part, you are translating 3001. So you have like a 4 by 4 unit matrix, but then the translation of 300 joins it. And then P2 now, P2 then becomes 5421. All right. So I suspect P2 should be T times. the same P1. T times P, the original P, and then we have 5421. And then the next thing you have the view transform, which is now, so you do the camera thing. Since camera is at 005, so you're going to change the world at opposite the camera, and you have 00 minus 5. So then you have P3 to be 54 minus 31. All right. So it's more like V multiplied by that original P. So, so that's how the transform pipeline goes. So then we go to talk about homogeneous coordinates. You know, those are the two things when we talk about linear algebra in computer graphics. So we talk about the homogeneous coordinates now. So homogeneous coordinates extend 3D vectors to 4D, right? So pipeline transform, like with length, project 3D to 2D, but homogeneous coordinates extend 3D of vectors to 4D. So that means you have XYZ mapped to XYZW. Usually W is 1 point, and I mean W equals 1 is point, while W equals 0 is direction. So now the question is, why do we talk about homogeneous coordinates? So with that homogeneous coordinates, right, we have that x prime equals x plus t sub x, and this is not linear. So with homogeneous coordinate, translation becomes a matrix operation. So all transforms become linear in that case. So, and it's easier to handle things. I mean, matrices operate in the realm of linear algebra for sure. So translation using homogeneous coordinates. Now imagine T is you have, just like what we've been having before, it's like you have a 4 by 4 matrix normally, but then whatever transformation you want to do, you put it on the last column. So you have tx, ty, tz, so that xyz1 is mapped to x plus tz, y plus ty, z plus ty. I mean z plus tz, comma, this one you now have right here. So that's using homogeneous coordinates. So if you now have a general 4 by 4 transformation matrix, so imagine M is R11, R12, R13, R21, R22, R23, R31, R32, R33. Then you have this one there, 0001, and then you have the transformation thing, TX, TY, TZ. So where R, the whole R now talks about rotation and scale, while T talks about translation. So you have rotation here, and you have translation right here. So now perspective, projection, and W. So projection changes W. So after projection, you have X prime, Y prime, Z prime, W prime. Respective divide now gives, okay, I think same thing like before, these things are not, they are different expressions. So it's better to have it this way. So now we have perspective divide. Now you have x equals x prime over w prime, y equals y prime over w prime, z equals z prime over w prime. So for perspective divide, now what happens? Given p is 4, 6, 10, 12, 10 2, divide by w. So w now is 2. So if you divide 3 by 2 now, you have 2, 3, 5, 1. So the point appears closer. So this point now is closer to the origin when you do perspective divide. So talking about points and directions, so if you have point P, which is 2, 3, 4, 1, which will 2, 3, 4, 1, right? And then you have a vector V, which is 2, 3, 4, 0. So translation affects points, but not vectors. So in this case, now we have XYZ 0 equals XYZ 0 like that. So you see 2, 3, 4, 1, 2, 3, 4, 0. So you have this, so T rather, T multiplied by XYZ 0 will give XYZ 0 also, because translation affects points, but not the vectors. So question, why homogeneous coordinates enable pipelines? So now we see homogeneous coordinates and pipelines coming together. So all transformations are 4 by 4 matrices, for instance. So model, view, and projection use the same format. They can be multiplied together. So like we said, in this order, you have the model matrix, you have the view matrix and the projection matrix giving you the MVP. So in that case, you have only one matrix applied in shaders. Example now, imagine this, given P to be 1, 1, 1, 1, operations, you scale doubly, you translate to 0, 0, and then you have the perspective projection. So for scaling, imagine you have 2, 0, 20000 to 2000 and 0001. So that means you have 2221, more like diagonal matrix containing 2221. Then if you can translate that. So for the translation, we said 200, right? So here you have the 4 by 4 matrix, except that for this first row here, you have 200 here. In this case now, This results to 4221. And then you have the projection. So for the projection, we have perspective projection. So for projection now, which is simplified, if you say W is Z now, so you have 4221 going to 4222 like that. So then if you divide by W, you have 2111. And the final 2D point is just 2 comma 1 like this. Okay. So the key takeaways we see in this whole thing is that in pipelines, objects pass through multiple spaces. Then MVP matrix combines transforms, and the other matters too. So you have projection matrix dot the view matrix dot the matrix, projection matrix, view matrix, and model matrix. So for homogeneous coordinates, we add a W component, and this enables translation, enable perspective, and makes transforms linear. Okay, so the mental model in this whole thing is this: think of graphics transformation as put everything in 4 dimension, and then you move it with matrices, then project it back to 3D and 2D like that. So you can check some practice problems right here. Solve our problems using homogeneous coordinates and 4 by 4 matrices. So we already see the process. Given point 2 minus 131, translate by 4 2 minus 1, find the new coordinates. So of course, for the whole translation thing, you're going to form a 4 by 4 matrix, of a 4 by 4 unit matrix, but on the last column, you put 4 2 minus 1, and then you multiply by this p. And then, you follow all that step. So then for scaling now, p is 1 2 minus 1 1. You scale sx is 3, sy is 2, sz is 0.5. Find the transformed point. So again, you do that same thing like we saw there. So for 3 and 4, you have something similar. Rotation about z-axis. Rotate by 90 degrees counterclockwise about the z-axis. Find the new coordinates. The model matrix construction, scale by 2, rotate by 90 about the z-axis, translate by 130, write the model matrix M, scale the correct multiplication order. Okay, so that MVP thing. Then for 5 and 6 now, okay, 6 looks long, so okay, yeah, I think I can still accommodate both. So for 5 and 6, view transformation, the camera is located at 008 and looks toward the origin. Write the view matrix. Of course, the view matrix is going to include something like 00 minus 8, because you have to change the world in front of the camera instead of changing the camera itself. Then you have the MVP application. You can follow that. Then 7 and 8, now you have the perspective divide. So after projection, the point is this: perform the perspective. I find the normalized coordinates. Of course, that's like dividing 3 by 2. You have 3, 2, 5, 1, and all that. And then you can then normalize. So point versus vector, you have P is 3211, V is 3210. Apply transformation, translation, compare the results, explain the difference. Then we have 9 and 10, which talk about composite transformation and full pipeline. So then you go the whole process. So try, okay, I guess I need to show them each separately. Okay, so scale by 2, translate by 030, translate by 200, compute the final coordinates, then write the combined matrix. So you can follow what the examples ahead before now. Then for the full pipeline now, so this is a point mo in model space is 1021. Then you have MVP. So you need to compute MVP. You're multiplying everything together. Then you can find clip coordinates, perform perspective divide, and give final NDC coordinates. I mean, that's where you do all this X prime, Y prime, Z prime, W prime kind of thing, right? Okay, so with this, we come to the end of this interesting video about linear algebra in computer graphics. So you see that next time you're designing a game or working on some pictures or videos and all that, algebra, know that you are dealing with matrices indirectly or even directly, right? So matrices are underlying all of these things. So all the pixels you talk about and everything, they are actually matrices. So you're having a lot of rotation, reflection, share, and things like that. So as you do all of that, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't, of course, you want to do that right away. And hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel. That gives you some special privileges, like, you can get PDF copies of my notes. You can actually get to see some videos first, or only you get to see some videos as members. I can consult for you on something that interests you on my channel, and so on and so forth. So don't forget, you can use that opportunity. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.